Welcome to chapter 23. We're going to talk about electromagnetic induction and transformers and motors and generators, so all kinds of cool things. I'm anticipating that there'll be 3 videos for this chapter, but maybe only 2. All right, so to start with, we have Michael Faraday to thank for showing us that you can produce a current in a wire without actually connecting it to a power supply. He thought that if you had a large enough magnetic field and you brought it near a coil of wire, that you could induce an electric current in the coil. And to verify this, he connected his coil of wire, we'll call it the primary coil, to a battery. And when he took a second coil of wire, we'll call it the secondary, and he connected that to a meter. So it's an ammeter, which measures current, or in the days before digital meters, we used what was called a galvanometer. And this was an ammeter that instead of only measuring one direction, its zero is in the middle and it could swing right or left. Now we've got digital meters and we don't have to care which way it swings. If our current's going the opposite direction, there'll be a little minus sign for us to look at. So anyhow, what Faraday discovered is that the only time he was able to get a reading on his galvanometer or his ammeter was at the instant the switch was thrown, when it was turned on and when it was turned off. So apparently it wasn't the size of the current and the associated magnetic field that created the current in the secondary coil, but it was a changing magnetic field that created this distant current for us. And we've been able to use it to our advantage ever since. So yay, Faraday. So when we are looking at currents and wires and magnetism, we need to talk about Lenz's law and magnetic flux and all things associated with it. So in magnetism, the density of the magnetic field lines gives us a measure of the field strength. So we refer to the magnetic flux as the total number of magnetic field lines passing through an area. And we symbolize it by the Greek letter phi, and we put a sub b on it. So this is a circle with a line drawn through the middle of it, phi sub b, and it's going to equal b times a times the cosine of theta. B is the size of your magnetic field in Teslas. A is the cross-sectional area that you're looking at, and theta is the angle between the magnetic field and the normal to the surface. Remember, normal to the surface makes a 90-degree angle. So here, this dashed line is our imaginary vertical line. The oval is our cross-sectional area. The diagonal lines coming down are the magnetic field, and this angle is theta. So the flux, the magnetic flux, is BA cosine theta, and we measure it in Webers. Webers are our unit of measurement. If we think back to Faraday's experiment, we discovered that the induced potential, remember potential is a voltage, depends on the number of coils in the secondary and on the rate at which the magnetic flux changes. So if you can change your magnetic field very quickly, you'll create a large current in the wire. If you change it very slowly, you get a small current. So Faraday's law of induction is that the EMF is equal to minus N times the change in phi divided by the change in time. You do not need to memorize this equation. We're not going to calculate things with it. I just wanted you to understand what we were talking about. And so the minus sign is there because of something called Lenz's law. Lenz's law says that a change in flux through a loop of wire will induce a current whose magnetic field acts to oppose the original change in flux. You know, oftentimes in nature, change is opposed. And so electricity is no different. If you, we create currents to create magnetic fields. And then when those magnetic fields are in place, opposing currents and magnetic fields will be created to try to neutralize the effect. And we can demonstrate this in the real world by using a magnet. If you took a magnet and you moved it up and down through a coil of wire, not connected to a power supply, but just connected to an ammeter to measure the current in the wire, the bar magnet and the loop of wire, as they become closer together, the magnetic flux changes, and that induces a current in the wire to oppose the change. So we've got a little diagram from the internet. If you've got a bar magnet in your hand and you push it up through this loop of wire connected to your galvanometer, remember that's just an ammeter that can go positive or negative. If you push up, the change in the magnetic field is going to induce a magnetic field around the wire to oppose it. And that magnetic field, that changing magnetic field, will produce a current in the wire, and we'd be able to measure it on the ammeter. Now, the really cool thing about this is if you change the direction of the magnet, the direction of the current will switch. And so we have a diagram from your textbook which shows you if the bar magnet has north at the top and we push up, the current in the wire is going on the front part of the wire to the left, and we'll have the galvanometer swing to the right. If we have the bar magnet and we pull down with it, it switches the direction of the current. If we turn the bar magnet upside down, so instead of north at the top, it's south, and we move up with it, instead of creating current to the right, like we did in our first instance, we'll have current to the left because we've turned the bar magnet upside down. If we take that upside down bar magnet and instead of going up with it, we come down with it, the current goes to the right. And if we let the bar magnet sit perfectly stationary, there is going to be zero current in the wire. So to change the flux, you can change the external magnetic field, so you can move the magnet closer or farther away, or you can use a stronger or weaker magnet, or you can change the orientation or position of the wire. You could take the wire and move it closer or farther away from the bar magnet. So all we need is that the wire experiences a changing magnetic field, and that's going to induce a current in the wire to oppose that change in the magnetic field. And we find applications for this in motors and generators and audio and video recordings and the magnetic strips on credit cards and cochlear implants and all kinds of things out there. It's an amazing world where you don't actually have to physically connect with a wire in order to produce a current. So you will need to know the equation for the motional EMF, and that's that the voltage is equal to BLV. So the voltage, or the EMF, is equal to BLV. Capital V is the voltage. It's measured in volts, or the potential, if you will. Capital B is the external magnetic field. It will be in Teslas. This script L is the length of the conductor that's in that external magnetic field, and it'll be measured in meters. And lowercase v is the speed with which your conductor moves through the magnetic field. So big V is the voltage or the EMF or the potential. Little v is the speed with which you're moving things around. So when you have a changing magnetic field, you're going to have a changing electric field. And so E is going to equal little v times B. So E is the electric field, little v is the speed of your moving charge, and capital B is your magnetic field. We will not actually be calculating with this equation. You don't need to memorize it. I just wanted you to know where the terms were coming from. So you can conclude that a changing magnetic flux produces an electric field. Eddy currents, and these are sometimes called Foucault currents, are circular electric currents, and they're induced inside conductors by changing magnetic fields in the conductor as a result of the Faraday law of induction. So eddy currents flow in closed loops within the conductors. They're in planes that are perpendicular to your magnetic field, and they can be induced within anything that's close and stationary as long as you have a varying magnetic field. You can also create them by some sort of relative motion between the magnet and the conductor. And in fact, we will be doing a lab exploring these eddy currents. We'll have a magnet that we can drop, so that'll be our varying magnetic field, and we'll have different kinds of material we'll let it drop through. Some of them will conduct electricity, like a tube of aluminum foil or a copper pipe, and some of them will be non-conductors, like a PVC pipe or a paper tube. And we'll just see what differences we can observe. So the magnitude of the current in a loop is going to be proportional to the strength of the magnetic field, the area of the loop, the rate that the flux changes, and it's going to be inversely proportional to the resistivity of the material. So it depends on what material you have, how fast things are moving, and how big they are. This diagram is from your textbook as well, and it shows an interesting result. If you have a swinging pendulum and you have a solid one, you have one with open slats in it, and you have one that is a non-conductor. So A is a solid conductor, B is a slotted conductor, and C is a non-conductor. If you let that pivot swing through this magnetic field, what you can end up with are eddy currents in some instances, and you will have different scenarios depending on what's going on. So if it's a solid metal, that's our first diagram, and we allow it to swing between the plates, the pendulum is going to slow down, and it may even, if your magnetic field is strong enough, it may even stop it. If the conductor is slotted, if it's got openings in it, it'll swing through, and it may slow down a little bit, but not very much, and it'll continue to swing. If you have a non-conductor, it's not going to slow down at all. It's like the magnet's not even there. So why is all this happening? Well, the moving metal, the moving conductor experiences a changing magnetic field, and that's going to induce an electric current that'll have a magnetic field that will oppose the motion. So this is all about Lenz's law. In your slotted one, the middle diagram, each little metal section has an induced current, but it's opposite from the one next to it. And so they cancel each other out, and it's as if it's a non-conductor. And then the very last one, the non-conductor, well, it doesn't feel the impact of that changing magnetic field, and there is no induced current in it because it's a non-conductor. It doesn't show induced currents. So what are some of the uses for these eddy currents? Well, we use them for what they're called magnetic damping, and you can use them in the laboratory to have a balance slow down the sway. We don't have them in the physics lab, But sometimes in the chemistry lab, the old-fashioned balances would use it to have it zero out quickly. Trash separation at recycling centers uses eddy currents. Metal detectors can use eddy currents, and the braking systems for trains and roller coasters use it. And induction cooktops, which you don't see so much anymore. They were very fashionable at one time. There are a series of videos on eddy currents and magnetic damping. And I'll try to put these links up separately on the chapter assignment site for you to look at. We're going to stop video 1 here. And we will pick up with motors and generators in video 2. So I'm going to stop the share, and I'm stopping the